Hey y'all, welcome back to Candidate Planet. I'm Lucen Mendel, and I'm kicking off a series on interview tricks. In this video, I'll be sharing an interview trick involving arrays. The trick is to be able to recognize when to iterate through an array sequentially and when to use index math. I'm going to show y'all a bunch of problems that involve different kinds of index math so that you can recognize these problems in the wild. And I'm going to show you what the code looks like so that when you're practicing and when you're interviewing, you have a high level and high quality template to start with. Let's get into it. Most of the problems I'm going to show you involve multi-dimensional arrays, but you can use this interview trick on a single one-dimensional array. So let's get that out of the way first. Here's the problem, and maybe this is a sub-problem in a more complicated interview question. But let's suppose you're trying to find an element in an array. Now, if those words in that array are unordered, then you kind of have to look at every single element. And it doesn't matter what order you look at them because they're out of order. So you might as well just iterate through the array in linear time to find what you're looking for. But if that array is ordered, you can use that information to save time. And this is where, for example, a binary search could be used. If you don't know what a binary search is, go and look it up. The point is that you can implement a binary search on an array by doing index math. Now let's make things interesting. There are a bunch of interview questions that use two-dimensional arrays. And there are 3 interview tricks that I want to share with you. First is finding immediate neighbors. Then we're going to review finding more neighbors using index math. And lastly, I'm going to cover blob detection. Before I dig into the code, I want to review what some of these problems look like so that you can recognize them in the wild. The point here is that even if different words and problem setups are used, the solutions and the code you write will still effectively be the same. So some of the two-dimensional array problems that you might get, they might involve grid-like data, for example, image processing, maybe for robotics, like detecting shapes and navigation, and whether that's LiDAR sensor input or camera sensor input. You might get a map problem that involves two-dimensional arrays. You can also get map problems that are represented as graphs, nodes and edges, because streets and intersections aren't necessarily laid out carefully in a grid-like system, but maybe you get a map of New York City or something like that. You can also see two-dimensional array problems come up in arcade games. Again, grid-like data, so something like Snakes or Space Invaders or any of those old arcade games with two-dimensional grid layouts. The last domain that I want to bring up is cellular automata. If you haven't heard of Conway's Game of Life, go look that up. It definitely comes up in computer science, and so it can show up in data science and algorithm interview questions. Okay, let's start with the first interview trick on two-dimensional arrays, checking nearest neighbors. Before you start writing that code, one thing you'll want to clarify is who is considered a neighbor. Is it just the cardinal directions, north, south, east, west? Or are diagonals also included? I'm going to show you a bunch of code templates that you can use when you have to find nearest neighbors. Here's a simple one, especially for cardinal directions. You have the function, it takes the board or the grid or whatever, and the row and column indexes, and it returns the indexes of the north, south, and east, west neighbors. And it's just doing that using index math. By the way, there's 2 little interview tricks I want to point out here. One, I like to use row and column as my variable names because when I use X and Y, I always get confused. Is it going to be board YX or board XY? But for me, I just naturally know, oh, when I first index into board, that's going to be the rows. That's what makes sense to me. You do what makes sense to you so that you don't get confused during an interview. The second little trick here is that I've used spacing to make it obvious what's happening. So this reduces the chance that I'm introducing a bug. It makes it easy for me to review real quick, make sure there's not a copy paste error. So use whitespace to your advantage. Here's what this find neighbors function looks like when diagonals are also considered neighbors. Again, I've used this whitespace to try to make it really clear to myself that I've taken care of all of the nearest neighbors and that I'm not counting myself. By the way, I'm not including boundary checks here just for simplicity, but you'll probably want to put boundary checks inside of these functions. Those boundary checks can start to get a little complicated, so here's another way to write this find neighbors function. This function is going to do the same thing as those other functions, return a list of row column tuples, but it's going to do that programmatically. So we have these two nested for loops that are calculating those row and column deltas. And then assuming that we're not looking at the initial center cell that we passed in, we're going to append those that row and column tuples with that delta added. So it's going to give us the same list. It also becomes a little easier to add in those boundary checks. And in this case, we're going to avoid adding neighbors that are off the board. Even once you do a quick read through and a quick scan to make sure that you're actually adding the column delta to the column and not the row delta, you can still run this code and give it a quick test. That's the advantage of putting this sort of thing in a function. Here, for example, as soon as I wrote that function, I wrote this print line, and you'll notice that our row and column requests are completely off the board. This was before I added those boundary checks, and I just wanted to see that I was getting the right answer. And I could have called it with row equals 1, column equals 1, and then I would have seen all these combinations where the row and column were quite similar. And so if I had mixed up my indexing, I wouldn't have been able to discover that. It would have been masked. So by calling this print with row equals 10 and column equals 100, I'm getting indexes that are just in a totally different space, but they're still easy for me to read and see those 901 endings to make sure it all works right. So again, that's trying to be strategic with your test cases. As soon as I add in those boundary checks into the function, of course, I'm going to need to update my test and just make sure that those boundary checks are working well. If you want to learn more interview tricks to be speedy and efficient, especially in the programming portion, check out the problem solving video that I made last week, and I'll put a link in the description below with a timestamp specifically to the efficient programming component. Let's move on to checking neighbors with more math. I don't want to spend a lot of time here. I just want to point out that in addition to finding the nearest neighbors, you can also do more math to find neighbors along a line. For example, you can keep incrementing the row or the column in order to find neighbors horizontally or vertically. You can also increase both of them, and then you get the neighbors along a diagonal. You can also implement something like a binary search. If the two-dimensional grid is ordered in some fashion, you can skip around to find what you need. The last kind of index math problem that I want you to be able to recognize is blob detection. What this means is you want to figure out how big is this shape, or what are the boundaries, maybe for image processing, maybe for figuring out how an autonomous vehicle will go around a wall, maybe it's part of some kind of game that you're building. And the way that you often go about this is once you find a cell that is part of this blob, like maybe you're trying to figure out how big is the green blob in this image. Once you find a green cell, you then want to recursively do a depth first search or breadth first search. It can be recursive, it could be iterative, however you like to get these things done. You'd like to expand your search space to find all the boundaries of that blob. Maybe you want to return a list of indexes of the tuples for all the elements in this blob. So what that looks like here is I defined this collection that we're going to pass through to the recursive function. And by the end of calling this recursion, by the end of doing all this blob detection, our blob collection is just going to have all of the elements in it. And then we can return those keys or the number of elements or return the actual elements. This is just a template that you can use. This helper function is where we do the actual recursion, where we have our inductive step and our base cases. Here, the first thing I do is put this element in our visited list and also inside of this blob collection, because that's what we're trying to figure out. Then we're going to do the inductive step, which is to recurse on all of our valid neighbors. We get all of our neighbors. We check to make sure that they're alive in cellular automata or that they're the right color in the blob detection. We also check that they're not in our visited collection. And then we recurse on them. It's going to add those new neighbors into our blob because they were valid and look for those neighbors and so on recursively. That's it, y'all. If you found this video helpful, please like, subscribe, and share it with your friends. If you have a candidate or employee question that you'd like an honest inside answer to, send me an email, lucen@candidateplanet.com. Thanks for watching, y'all. See you next time.